Hello everyone, this is Spencer Snowling and welcome to today's webinar where we are going to be discussing pumping models and energy consumption and how you can use the GPSX pump model to analyze different ways of controlling the energy usage in your pumps, to look at different pumping options, and we are going to cover ground that we presented in a presentation at WEFTEC last fall, and a small case study that will explain how you can use those calculations to evaluate energy savings and cost savings. My name is Spencer Snowling. I'm Vice President of Product Development here at Hydromantis. And as I mentioned, today's presentation is based on a paper that was done by my colleague Rajiv Goel here at Hydromantis and Stellian Iannulli of ASI Consult. And if you have access to the WEFTEC proceedings from last fall, you can download the paper there and see a lot more details than I'll be able to present in my short presentation today, but it is there for you to take a look at if you can. So the plan today is to talk a little bit about energy usage at wastewater treatment plants and a little bit of a background about the energy calculations that we do in GPSX. There's a whole webinar that I did on that actually last year. If you want to look at that as well, I'll cover some of that same material again today. We'll also talk about the pumping model itself. The pump model is a special version of the pumping that we do in GPSX, where we took that type of calculations that we were doing for figuring out the amount of energy required to pump a certain amount of water at a flow rate against a certain amount of head. And then we expanded that model so that it could be used to evaluate the differences between operating a number of pumps at constant speed, or if you had a variable speed pump or pumps, and looking at those strategies. And that's what today's talk is going to be about. And I'll show you the details of that model and where you can find it in GPSX. And then lastly, Rajiv put together and Stellian put together a nice little case study that compared those two options against each other and show them how those sorts of things pan out for different kinds of loading to your wastewater treatment plant. So first of all, as we all know, wastewater treatment is a very energy intensive operation. Oh, I'm sorry, I forgot to mention that as always, if you have any questions as we go along through our webinar here, you can type them into the GoToWebinar dashboard. There's a questions panel there which you can open up and pop out. And if you have any questions along the way, feel free to type them in there, and then I will answer those to the best of my ability when we get to the end of the webinar. So as I was saying, energy consumption is a key element of operating any wastewater treatment plant, and as you probably know, aeration, as we can see here, the amount of air that's required to do the mixing and drive all these bubbles that we see in the overhead view of these aeration basins here is quite significant. It can make up to about 50% of the total energy cost to run a wastewater treatment plant. But second to that is usually the pumping of the liquid itself. So a large number of wastewater treatment systems require lift stations as the sewage is delivered into that plant, and you have to get it up to grade. Also RAS pumping, of course, and any other type of internal mixed liquor recycle pumping and so on. Those all require energy, and they all need to be assessed in a way to understand how that energy consumption is part of your system. So we know that, of course, in the trends right now in our industry is to look at energy reduction as it has always been, but with the goal of hopefully getting to energy neutral wastewater treatment plants, to be able to generate enough energy that you have at your plant from energy capture and digesters and burning digester gas and so on, and also reducing the amount of energy that you are using to try and offset and see if we can get to the point where we can have that treatment pay for itself. So as part of that, there is a big move afoot, of course, to do energy benchmarking to understand how well you're doing at your wastewater treatment plant in order to see how well you're doing compared to other treatment plants of similar style and size. And as part of that, there is methods to estimate the costs and benefits of different operations of your wastewater treatment plant. And of course, simulators are part of that. So we see quite a few people using GPSX to do wastewater energy consumption and generation analysis. It certainly has been part of the use of the software almost my entire career at Hydromantis here for almost 17 years now. So, but really the number of people doing it has really risen quite a bit in the last 4 or 5. So we know we're sort of moving into an area where it's of utmost importance now. So as you may know, the way that we calculate the energy consumption in GPSX is to take a look at the calculations that were already there to do that process analysis. So you have a loading coming into your wastewater treatment plant, and we're doing a mass balance on the COD and the nitrogen and phosphorus and so on. And all of that information is there in the model. So this little line here at the top represents essentially all of the things that you would normally find in GPSX when you're doing a wastewater engineering analysis. So the loading into the plant, the size of the tanks, the way that they're being operated, do they have a DO controller, what's the oxygen transfer efficiency, and all of those sorts of things that describe how much blower activity has to happen and how much pumping has to happen. And we ask for, in our operating cost menus, information too about the head that you're pumping against and the efficiency and so on. Then in those operating cost menus, we actually ask for a number of other bits of information, and we've been slowly expanding these the last couple of releases of the software to include things like mixing energy, and even in the tools section of the unit processes, you could put down buildings there that are really there to reflect the accurate use of energy at a wastewater treatment plant that's not directly connected to the wastewater treatment process itself. So the idea being that we can get a whole plant energy consumption, hopefully. So anyway, all of these things are taken into account: the pumping, the aeration energy, the mixing, and the heating, and so on. And these things are taken into these energy models, and that is they're calculated on a unit process by unit process basis, and they're dynamic in the sense that they continuously evaluate the pumping going on, instantaneous amount of pumping going on at any point in time, and calculate the amount of energy, instantaneous energy required to make that happen. We also have energy price models, which I'm going to come back and touch on later, and energy emission models for our greenhouse gas library, so that you can even look at another layer of depth as well. And I won't be going into our greenhouse gas calculations today. We have an entirely separate webinar recording on our YouTube channel about that, and if you want to know more about it, I can direct you over there, or I can follow up with you after the webinar today. So when you're calculating the performance of your wastewater treatment system, and you've put together a plant that looks something like this in GPSX with primary clarifiers and activated sludge tanks and secondary clarifiers and so on, for any model that you make in GPSX, you can calculate, or the energy consumption will be calculated for you automatically. You may want to go in there and calibrate it, but it's not, it's a built-in part of GPSX, and it actually has been for all the way since version 4 of GPSX. So you can calculate a graph that looks like this that'll break down on a unit process by unit process basis, the amount of energy being generated or required. You can then break that down into tables and graphs, and I'll just very quickly pop over to GPSX to show you how you access that in case you haven't had a chance to take advantage of those particular features in our software. So this is actually one of the sample layouts. If you go to the sample layouts menu here and you select under the software features our energy and price, energy and costing example that we have there, and then you run that to steady state. And then what you can do is pop up here to these buttons that are up here in the corner. This is our Sankey diagram. That's for tracking mass flows throughout your wastewater treatment plant, and the energy consumption button is the one that's right next to it. It's supposed to look like an electrical plug, so you hit that, and what that's going to do is give you the opportunity to investigate energy usage as broken down into several categories that we have in this menu here. So you'll find just the aeration power. Since these are anoxic and anaerobic tanks, there's no energy being used for aeration here. Pumping power, we can see the RAS pumping here is fairly significant. And we can look at mixing power and so on. And these are all taken into account and added together to get total power. And so you can see here, the higher the number, the higher the shading color and so on. And if you flip over to the table and pie view here, you also get that same kind of breakdown. And you can click on any one of the unit processes to get a breakdown of its energy usage for that particular one. Or if you click on the bottom, you get the entire plant layout energy usage as well. So just a little quick summary to where you find all of that information in GPSX. Okay, coming back to our discussion of energy calculations, just to summarize very quickly as well, we have a fairly sophisticated energy consumption model that is tied in with blowers. And so I'm mostly going to be talking just about pumps today, but just to let you know that we do have a sophisticated blower model as well in terms of the energy side, and you take, as I mentioned before, the typical things that you would normally do, all of that's going to be built in, taking in the flow rate and wastewater characteristics and that loading and so on. The biological model, of course, will predict what the oxygen requirement is with the OUR, and then you can use your transfer model either working from specifying an airflow rate or specifying a dissolved oxygen concentration with your DO controller, and those sorts of things will transfer a certain amount of oxygen to that system, and then of course that predicts performance. So, but this here can then subsequently be used to calculate the amount of that oxygen transfer. Then is calculated in the amount of energy that's required to do that for blowers, and we ask for some details about efficiencies and head and so on as well. And so they're all for a default diffused aeration system like this one. We do have even one more level now in GPSX, which is our air delivery model, which now adds on the main piping and the drop pipes and so on, and valve positions and valves that control the distribution of the air in that activated sludge tank. And we now have models around those too. Now it's a special object in GPSX. In addition to the regular plug flow tank, you can get the plug flow tank with aeration header. It's actually the next object on the menu there. And you can do that as well. So both of them have exactly the same model in terms of oxygen transfer, and they have the same model in terms of biological calculations, but you can get more details about the way the aeration is being delivered and how efficiently that is being done. Okay, so that's aeration. So now we're going to get on to the main topic of today, which is talking about pumping water. So the way that we've done this is that we've tried to allow people to specify pump curves for the various pumps that are being used in GPSX. And you can define a system curve as well, and that allows you to define the efficiency of your particular system. Are you having to throttle back? Are you wasting any potential energy here by defining those two particular things? So now, just a quick summary of the terminology that I'm going to use today. Here's what the pump curve is going to look like in blue here. So this is flow on this axis and head on this axis. And we can see here that for a given pump of a specific design, we can know what this particular curve is going to look like. That's a lot of information you can typically acquire from vendors and so on. And that pump curve defines how much head you can push for a given flow rate. So now the system curve is the other relationship, and it's the intersection of these two things that defines the operating point that you are at. So now most pumps are designed for a specific operating point. And if you were to before we move on, define that the system curve here is made up of two parts, the static head and the dynamic head. The static head is really looking at the difference between elevations. If you're pumping, up against a certain amount of elevation, it's defined there. The total static head is the difference between the two elevations that you're pushing to. And the dynamic one is actually a function of Q. It's a function of the flow rate. And those two things together define what that system curve is. So it is a function of the flow. And it is a function also too of the distribution system and the pipe sizes and a number of other things as well. Okay, so the point that I wanted to make was that these systems have a specific design flow, and if you have to pump a different amount than that, if you were to say the system that we've got defined here, if you were to reduce the amount of pumping here down to a lower amount, we can see that that operating point will slide away from the design point over here to a new point that is corresponding with that new pump flow rate. And by doing that, we can see now here that the amount of head required in the system is a lot less than the head that the pump wants to push out. So it requires, valve throttling to be able to achieve that particular thing. And there's a certain amount of energy wastage associated with doing that. So you're not operating at the most optimal point. So the option is, if you had a constant speed pump, is bring more pumps online. You can have pump curves for an individual pump, and if you combine them together, it works basically the same way. You have this combined here. If you had a couple of pumps that were defined by this particular curve each, and here's our static, our dynamic and static head together, the system curve here, and we can see that you can reach a higher point on that curve if you have to by operating two pumps together. So, but the problem still exists in the sense that if I have to move to a point that's farther away from that design, then there is going to be that difference between the operating head that the pump is going to provide and what the system will require. And so you still have a bit of wasted head there. So although it might be less than if you were doing it, of course, with a single pump. Now, let's contrast that to doing it for a variable speed system. And you can see right away here that we have a pump curve defined right here, just like we did before. But in fact, a variable speed pump has a number of different pump curves. And so if we had to move to a lower flow rate, so if we had to go from this flow rate down to here, by just running at a lower pump speed, we can actually slide down to one of these lower pump curves and actually maintain being on that system curve there and have a new operating point that's down here where we're not going to be doing it at a sort of wasting a lot of energy by throttling back and forcing ourselves to waste the energy that would be the difference between here and here. And so this new system, by using variable speed pumps, allows us to be more efficient. Okay, so those things can be entered. Those two options are available in GPSX, and so I'm going to very quickly show you what that looks like. So let me just get rid of that previous layout, and you'll find the pump that has all of the ability to do the pump curve characteristics and so on down here in the tools collection of objects that are in our unit process menu. And you'll see here this particular pump object. So let's put that on the board. And if I right-click on here, we can define a lot of details about that pump itself. So I'll say very quickly, this pump doesn't actually do anything with respect to process. You can just run a flow through it. And what it does is it will represent, based on the flow rate that's coming through, all of the details around energy usage. So let's click on that pump curve pump data menu, and we can see here that we have the pump speed that we would be operating at for that particular pump that you have, and the number of points in the pump characteristics curve allows you to define this table. So there's 15 points, and you can see here that we can define for a given pump flow rate what the head and what the pumping efficiency is. Pumping efficiency is what we're using for the energy calculation. That those things are there in detail, and those will allow you to define what you want on your shape of your curve, and so you can come in and enter those things into GPSX. So the second step is then to illustrate for that particular pump whether you are going to operate this as a constant speed or whether this is going to be operated with a variable speed system. So you can do this here by clicking on for using variable speed pumps, in which case you can specify a minimum, a maximum speed that it can be operated at and some efficiencies for that. If you're using a constant speed pump, it has a separate efficiency that you would provide, and also you have to specify what that constant speed is. Now, what's going to happen is, I'll show you here shortly, is that you define this curve and this particular type of operation, and also we also do the same thing in another menu for the system curve itself. And then what you do is when you operate it, we will, in the background, change the amount of pumps that are in operation based on a certain logic, and then that way we can evaluate the amount of energy that's being used and also the amount of head that's being pumped against and whether we're being energy efficient or not. Okay, so back to the slides. So just a last few words about the energy calculations before we get into the case study. The energy model itself is a really straightforward calculation to get us from the pumping rate to the amount of power that's required. It's just this equation here. We can see it's a function of the flow rate and the amount of head that's required here. And that calculation is done not only in the pump object that I just showed you, but actually in every place that you see one of these little pump symbols in GPSX. So for a plant that you have, you can calculate an operating cost at any one of these particular points. And if you right-click on the object and go to the output variable menu and go to the operating cost menu, that's where you'll find all of this information. Okay, so when we move on to evaluating what the various methods would be for evaluating, operating this with a constant speed pump versus a variable speed pump, there are a number of spreadsheets that are out there for evaluating the static head, and those are available and can be calculated fairly easily. But of course, in GPSX, one of our main things is that ability to model things dynamically and to have the flow rate, for example, change over time. So we have a need for an accurate way to assess the change in the dynamic head as it moves around at different flow rates. So what we've done is we've put together two separate flow sheets here that describe the way that we choose how many pumps are going to be in operation at any given time. So I'm just going to quickly go through these. I'm going to do the constant speed one first. So after these characteristic curves have been defined, we take the flow that is coming for the model, and then we take a look at we use that flow rate to calculate the system head and the pump head, and then we calculate and compare those together. Is the pumping head that is required greater than the system head? If it is, then we have enough pumps online, so we're running okay. And if not, for a constant speed pump, where we only really have one option, which is to put another pump online, so we do that, come back around here, reevaluate the entire system again, and just keep going around until we have enough of these constant speed pumps at whatever speed that's already been fixed at, have that running in order to do the job. Now for a variable speed pump, we have more options, of course. So we go through that same type of situation. We calculate the pump head and the system head, and if it's not enough, we can actually turn up the speed of the pump first, and we turn that up, and we can change that pump speed, go back, reevaluate the pump side, and then keep going around until that particular pump has reached its maximum, in which case we can bring another variable speed pump on. We go back up, recalculate the entire system over again, and so we have the ability to bring them on and turn the speeds and change both the speed and the number of pumps online to be able to try and match that system head that is required. Okay, so those things are going to be compared side by side here in this little case study that we have. So this is what the plant looks like for the particular system that we were studying. It's an MLE configuration with the pump station here. We're going to be looking at the amount of energy that's required in this particular pumping station that was used to pump up and load that aeration system. So here's some of the data that we used. The pump curves look like this with that kind of data. And we had a system curve that was put together by Stellian based on calculated using K values estimated based on pipe lengths and fitting losses and static head and so on. So this is something that we also entered into GPSX along with two different loading patterns that we had for 2 different days. And so one of those was a wet weather event and one of them was a dry. So the wet weather event, you can see here, this is influent flow rate in blue, so it goes up quite a bit. And then, of course, the other rate is quite flat, the dry weather one, so we don't have a lot of dynamics in that particular one. Okay, so we're going to move on to looking at what that's like. We ran that system, we let the pumps, that pump operation logic do what it was supposed to do. And the best way to interpret what we have here, we're dealing with the wet weather flow first, is to look at the system head, and that is this dotted line in green here. And you can see that the variable speed system here, which is shown in red, the difference between what the variable speed was able to do and what the system required is actually fairly small, and it could match it relatively closely. Whereas the constant speed head was basically stuck with only having to bring extra pumps online to meet that minimum requirement, and as the flow went up and down during the day, that may or may not have provided a few like quite a bit of extra head pumping as well. So that's looking at head here. If we look down here on the power requirements, we can see here that with changing that flow rate here, changing as the loading changed during the day and the amount of pumping requirements changed during the day, we're comparing in red the variable and in blue the constant speed system, and we can see the difference between the two is how much was saved by going with the variable speed system. And actually this diagram over here is basically the integration, or just summing up those energy savings through that 24-hour period. So we can see here that overall the variable speed system in red had the lower energy requirements, and of course that makes sense because we could dial into very close to what was the actual amount of head required. Okay, so that was the dynamic activity during the wet weather event, and on the dry weather day, there's not a lot of fluctuation you can see here, and of course this is sitting at a point where the variable speed system can actually match that quite tightly. The constant speed is sitting up far above because it had to have more pumps on than was the minimum requirement. And so the power savings here is more constant throughout the day. And we can see, of course, that there's quite a big difference, and we integrate that over time, and we get, again, an energy savings for the variable speed system. So just taking those last two bottom right-hand corner graphs that we had and plotting the differences in the energy requirements, kilowatt hours over a one-day period, we can see that the energy savings for the wet weather event was 36%, and the energy requirements for the dry day was 42%. So, but you can even extend it beyond just looking at power and energy requirements by actually looking at dollars, by looking at the amount of cost savings. And that may or may not totally correspond depending on what time of the day that things happen. So you probably know that in GPSX that you can access the operating cost menu and set the price of energy to do various things during the day. So this is time-based pricing. You can have a constant price rate if you want. This time-based pricing basically allows you to specify different prices for different times of the day. So here we can see, for example, that here starting at, this is 2 days of time, we have a high cost during the day and a low cost at night, and back and forth and so on. So you can set the number of different tiers that you would like, and so on. We also have seasonal pricing, which allows you to do much more sophisticated pricing with different times at different points of the year, and even do something like this. This is 7 days, and we can see that the pricing can be very low on the weekends, and then even within one day there's sort of a mid and a higher peak level as well. That's all based on time, and this is pretty much exactly how the pricing works here in Ontario where I live. And so those were applied in this particular case study as well. So if we compare the two situations again, day one was the wet weather one, and we can look at for a constant electric price and a peak price, that basically they give you the same types of savings. And really what that's implying is that most of those savings took place during the off-peak price anyway. So those two particular systems, or particular pricing methods, basically worked out to the same thing. However, for the one that was more constant during the day, where the savings was pretty much evenly spread across the 24 hours, if you have a peak price model, we can see here that that is making a big difference. And in that case, that's really implying that the energy saving was happening during a time when there really was some cost effectiveness to going with that, like it was sort of combining the energy savings along with the good pricing, the good timing of the pricing at the same, combining those two things together to get 57% over just the proportional savings of 36% energy. Okay, so I realize I've come right down to my last few minutes here. Just to quickly wind things up, GPSX has these models that are built into all of the objects for you. We have that newer, I should say, it's been there for a couple of releases now, energy pumping model where you can actually go beyond just having a constant efficiency and actually enter in your own pump curve. And these sorts of things also, and that particular model, allow you to define fairly sophisticated sophisticated ways of operating those pumps, and you can do a lot of really interesting things with those.